output. The output can be represented. Suppose you know that LTI system, it has an n number of input and n number of output. So the output can be output k from 0 to n a k y n minus k. So output is equal to summation of k from 0 to m b k, summation of all delayed, the present, that means the present input signal as well as past input signal we can express. That's why if it is k is equal to 0, it is a present one, x of n only, and if k is equal to 1 to higher number up to m, it can be x n minus 1, n minus 2, n minus 3, etc. Those past values. So this is the differentiation of a linear time system. That means output can be expressed in terms of past and present inputs. So how you find the frequency response of this system? So frequency response is equal to h e raised to j omega. So we can find the h e raised to j omega. That will be the frequency response from the h e raised to j omega. That is from the frequency response. If you are taking the magnitude of h e raised to j omega, we can obtain the magnitude response. And if you take the angle of h e raised to j omega, we can get the phase response. So how we find the h e raised to j omega? So we can take Fourier transform of both sides. That means you can take the Fourier transform of the left hand side and right hand side. Then y e raised to j omega, it is equal to x e raised to j omega into h e raised to j omega, where h e raised to j omega is called the impulse or the transfer function, system function. So that means h e raised to j omega is equal to y e raised to j omega by x e raised to j omega. So h e raised to j omega, that means the frequency response of this system can be obtained by y e raised to j omega by x e raised to j omega. For that, we can take the Fourier transform of both the side. That means so Fourier transform of left hand side and Fourier transform of right hand side. Okay, so the system itself, it is a linearity because the system itself, it's a LTI system, linear time invariant causal system. So it obey the linearity property. So we can take Fourier transform by this one, that is summation of k from 0 to ak e raised to minus j, because a delayed element can be expressed as e raised to minus j the whole raised to k into y e raised to j omega, which is equal to summation from k from 0 to m bk e raised to j omega, same one, k into input x e raised to j omega. From this, we can find y e raised to j omega and x e raised to j omega. You can take outside. Then y e raised to j omega by x e raised to j omega, which is equal to summation of k from 0 to m bk e raised to minus j omega by summation from k from 0 to n ak e raised to minus j omega k. So this is the frequency response of this LTI system. I think we can go okay. Again, I think we can go a problem. Okay. Actually, this was taken earlier, but for the examination point of view, I have to take one more time. So next we can take a problem. So problem, consider a stable LTI system characterized by yn minus a yn minus 1, which is equal to xn. So yn minus a yn minus 1 is equal to xn. Find hn and h e raised to j omega. Hn is the impulse response. Find impulse response and the frequency response of this one. For also from this equation, maybe they can ask what is plot the magnitude response and phase response. So magnitude response is you find the frequency response, then from the modulus of h e raised to j omega is the magnitude, and angle of h e raised to j omega is the uh, phase response. Okay. So taking the Fourier transform of both sides, what happened when you yn is take the Fourier transform y e raised to j omega, y into a into yn minus 1, that is delayed element, is equal to a constant into e raised to minus j omega into y e raised to j omega, e raised to minus j omega into y, because the one delayed element, it is equal to multiplication of e raised to minus j omega into its Fourier transform y e raised to j omega. And right hand side, this is only x e raised to j omega. Our aim is to find the frequency response and the what it is h impulse response. Okay. So h raised to j omega. So we can take the common factor of y raised to j omega. That means it's equal to 1 minus e raised a into e raised to minus j omega, which is equal to x e raised to. So y by y e raised to j omega by x e raised to j omega, which is equal to 1 by 1 minus a into e raised to j omega. So this is the what it is. This is the frequency response of this system. Frequency response of the LTI system. Or we can say that this is a transfer function of the system. H raised to omega is the transfer function of the system. So the frequency response consists of two plot. One is magnitude plot and phase plot. Magnitude plot is you have to take magnitude modulus of h raised to j omega. So that what is the magnitude? Magnitude is we take the modulus of this one, then we can apply different values of omega, and we can get the values in each omega value. So the omega can be varying from 0 to infinity, like that. So similarly, angle of h raised to j omega is a phase plot, so that we can take angle of 1 minus h raised to j omega, or we can say that angle of phase response, you can take that as tan inverse of numerators, or tan inverse of magnitude minus tan inverse of imaginary part, so magnitude response is the modulus of the numerator square root of divided by root of this magnitude of the lower part, that is the modulus of h raised to j omega. So in the phase is you take just angle of 1 by 1 minus a into e raised to j omega. For that you can take the tan inverse of your what it is in the first is take the real part minus tan inverse of imaginary part, or okay, tan inverse of imaginary, like that you can calculate from this h raised to j omega. So here they ask find impulse response. So impulse response is just to take the inverse Fourier transform. So this is a ready form, so that a raised to n, this is in the form of a raised to n into u of n. That is a impulse response. Okay. So here we have looking for a frequency response of a LTI system. So this is a difference equation. So from this we can find h raised to j omega, for that taking the Fourier transform of both sides, and from the from this transfer function we can calculate the magnitude response and frequency response. Together it can be known as the frequency response. Okay. So here if you are taking the inverse of h raised to j omega, which is equal to hn into a raised to n. So like that. like questions may ask them. Okay, another problem. This is also we done earlier. Same question. So consider a stable LTI system characterized by yn minus 3 by 4 yn minus 1 plus 1 by 8 yn minus 2, which is equal to 2 into xn. Similarly, you can find hn and h e raised to j omega. Then also we have to do the frequency response of this system, LTI system. Okay. So the thumb rule is, if them ask the h raised to j omega, you can take the Fourier transform of both the side. Y e raised to j omega minus 3 by 4 e raised to minus j omega. So this is the delayed form, e raised to minus j omega. If it is two delayed form, it is e raised to minus 2 j omega. So like that, 3 by 4 into e raised to minus j omega into y e raised to j omega plus 1 by 8 into e raised to minus 2 j omega. So it is the equivalent of the y n minus, so Fourier transform of y n minus 2, or delayed two place Fourier transform into 2 x raised to j omega. So from that, I can calculate, this is called the transfer function. So from the transfer function, you can take according to the numerator and denominator by y e raised to j omega by x e raised to j omega. Okay. So here we have splitting 1 minus 3 by 4. You can split as half e raised to j omega minus 1 by 4 e raised to j omega. So conveniently we can factorize in the lower term, so that we can equal to 1 minus, first term is similar, minus 1 by 4 e raised to minus j omega you can take outside, so that 1 minus half e raised to minus j omega. So that this term can be factorized by 1 minus 1 by 4 e raised to j omega and 1 minus 1 by 2 e raised to minus j omega. Okay, so this is the h e raised to j omega. From the h e raised to j omega, we can calculate the magnitude response. Magnitude response is nothing but the magnitude of h e raised to j omega. So here also magnitude of magnitude of numerator by denominator. So for that, we can calculate the magnitude. Magnitude is the root of, take root of real square plus imaginary square. The root of numerator, the root of real square plus imaginary square. Similarly, in the denominator also, root of real part and the imaginary part. Here it is factorized, but you can take. So from this, can take the magnitude response. So similarly, you can calculate the phase response. Phase is angle of h raised to j omega. So tan inverse, the real thing minus imaginary thing. So here we have, the focus is to find the hn, so that we can the denominator is factorized. Then you can take inverse Fourier transform. Inverse Fourier transform is partial fraction. You can apply the partial fraction. So a by the first factor and b by second factor, and find the value of a and b by applying proper values e raised to j omega. If it is 2, you can get the a value, and if it is e raised to minus j omega is equal to 4, then it can be equal to b values. So that we can take a and b. So we can conveniently taking the hn by direct applying minus 2 into this term. This term is a raised to n form. That is 1 by 4 a raised to n, 1 by 4 raised to n into u of n. So similarly, in the second part, 4 into half raised to n into u of n. Okay. So these are the different problems in the LTA system of fourth module, first one. Then previous one, how you find the magnitude when you take the root of real square plus imaginary square and denominator is root of real square plus imaginary square, then you have to draw a graph with respect to the magnitude of the y-axis. It is the magnitude of h raised to j omega, and x-axis it is the omega values. So we can substitute omega is equal to 0 and omega is equal to uh, in- starting from omega is equal to 0 to higher values up to infinity. Omega is equal to infinity. What is the value of the magnitude of the different values of omega? Similarly, in the phase response, you can phase response angle of h raised to omega is plotting with respect to the omega. So y-axis, x-axis is omega, and y-axis is angle of h raised to j omega. Then from this, you can find the find what find the values of phase response of different omega. And if the omega is in radian, you can put from 0 to 2 pi values. So this is okay. I think this h of n is okay, fine. So like that, you can finish the frequency response of a LTI system. So similarly, you can take other problems. Other problem that is in the, I think it is helpless to answer. Okay, this is called uh, consider a stable LTI system characterized by d by dt of yt plus a into yt, which is equal to x of t. Okay. So find ht and h raised to h j omega. So here they are not given any continuous term or a discrete time, but this is a differential equations. So differential equation is that is the continuous time signal can be represented in terms of differential equation. So we can feel that, say that this is a continuous time because this is the y of t. This is a continuous time signal, and we have to calculate ht and hj omega. So hj omega is the frequency response. Okay. Here also we can find the first we can find the transfer function. From the transfer function, you can calculate the frequency response. That is the difference of the earlier problem and this problem. So here also we can take the Fourier transform. Okay, Fourier transform again j omega into yj omega. J omega into yj omega. It's a delayed value or differential values plus a into y j omega, which is equal to x j omega. So this is a continuous time signal. So from that, you can calculate the h j omega y which is equal to y j omega by x j omega. Okay, so from this you can find this is the transfer function. Here also you can calculate the frequency response. Just to calculate frequency response is involving both magnitude response and phase response. So how we find the magnitude response? We take the modulus of HGJ, okay? So that this will be equal to modulus of 1 by A into j omega. Okay, so that is equal to, you can take the magnitude response real square, root of real square plus imaginary square, and denominator also root of real square plus imaginary square. So and the modulus of h e raised to j omega, which is equal to root of the real, the here there is only real time. So 1 square root of is 1 itself. So 1 by so this is now it is root of a square. That is real part square plus imaginary square. So omega square. So the answer is 1 by a square plus root of a square plus omega square. So you can apply different values of omega so that you can draw, you can plot the uh, magnitude response of this scene. Similarly, you can take the angle of h raised to j omega. So tan inverse of this one, numerator and denominator. First, you take tan inverse of real part by the imaginary part. So tan inverse, so minus, that is here it is equal to minus of tan inverse. Uh, Real part is a by imaginary part omega, a by omega. So here we can calculate ht, that is impulse response also we can find. So ht is equal to a raised to minus 80 u of t. Okay. Okay. Same problem. You can take this one. So consider a stable LTI system characterized by d square by dt square yt plus 4 into d by dt of yt and 3 yt, which is equal to d by dt of xt plus 2 into x of t. So on point of the time, our fourth module problem, they may ask, they may not find the h of t, they find what is the hj omega, or what is the transfer function. Then from the transfer function, you can plot, you can find the frequency response. For that, we have to calculate the magnitude of hj omega and angle of j omega, or phase response of this LTI system. So from this equation, we can take the Fourier transform of both sides, so that the first will be j omega square into y j omega, and second is 4 into j omega into y j omega, and third, this 3yt can be taken as 3 into y j omega. The right hand side, similarly, it is multiplied with j omega into xj omega plus 2xj omega. Okay, so from this we can find the transfer function which is equal to yj omega by xj omega. Okay, so this can be conveniently uh, take as 2 plus j omega and 3 plus 4 j omega plus j omega the whole square. So from this, how we find uh, magnitude response, or magnitude of h j omega, which is equal to, how you take the magnitude of numerator and denominator separately. So numerator is root of 2 square plus imaginary square, that is omega square. So 4 plus omega square root of the numerator, and denominator is, you can take 3 here, this is equal to minus omega, because j omega square is minus j omega. So 3 minus omega the whole square, root of 3 minus j omega the whole square plus imaginary term is j into 4 omega. So 16 omega square. So root of 3 minus omega square the whole square minus 4 into omega the whole square. That is the denominator. So numerator and denominator we can get, and substitute different values. Omega is equal to 0 values first. So that I can know that it is equal to 4 by y, 4 by 9 something. 4 by 9 maybe, when omega is equal to 0, and higher values of omega, so that I can plot a magnitude of h j omega versus omega. You can plot. So similarly, the angle of h j omega, angle here it is angle of h j omega, we can obtain by tan inverse of what? Tan inverse of real. This is equal to 2 by imaginary. Tan inverse of 2 by omega, the numerator, and denominator is tan inverse of 3 minus omega square by imaginary part is 4 omega. So tan inverse 3 minus omega square by 3 omega is the, so that together with, we can write as tan inverse of numerator minus tan inverse of denominator. From this, you can calculate the phase response. So this step, it is written like this because you have to find the h of t also. Okay. So in this fourth module, it is not an material. So or we can calculate this one by taking the inverse or taking the inverse Fourier transform by applying the partial fraction. Okay. In the fourth module, they are asking only to find whether to calculate the frequency response of this LTI system. So first you find the transfer function. From the transfer function, you can calculate the frequency response. The frequency response involving both magnitude and phase response. Magnitude response is, so taking the magnitude of hj omega, and phase response is angle of hj omega. Okay, clear? Clear? Hello? Any feedback? Can I draw because the limitation is, hello? Hello? Is it okay? So how to find the frequency response? മനസ്സിലായോ? Hello? How to find the frequency response of this one? Okay, so it can be taking, first you taking the hj omega or frequency response of or transfer function of this system. From the transfer function, you can calculate magnitude of hj omega. Magnitude of hj omega, and that is the magnitude response. And from this hj omega, this is okay. So these are the frequency response of discrete time system and discrete continuous time system. This is the continuous time system for its frequency response. Can I show better in a better way? Is it okay? Can I show?
Sure, sir.
So it is better to stop the presentation. Stop presentation. I will clearly explain one more so that I. Hello. So better to take a short break. ഒരു 15 minutes break കഴിഞ്ഞിട്ട് നമുക്ക് ഞാൻ കാണിച്ചു തരാം എങ്ങനെയാണ്. Okay.
Thank you, sir.
Okay.
Okay, sir.
10:45 now we can meet. So now what is 17 is there? 17? 17, 31, 41, 42, 47. 47 is okay. Here, okay. 47 wonder. 53, okay. Okay, 50 minutes and I'll arrange it.
53.
Stand